Our next speaker is Martin Levin from nearby Silver Spring, who will talk about an exhibit that you have here on Platonic.
Thank you all for being here. And we will just get set up a little bit here, and I'll apologize for what my daughter calls my ancient computer, which is giving you smeary images up there, but I think they will nevertheless do the job. So, just getting set up a little bit. 2 years ago, my son was driving me from his home in Brussels to the Bridges Conference in Enschede. And so I had a bit of a car ride to kind of muse about my experiences looking at mathematical art exhibits and listening to mathematical lectures and reading textbooks. And whenever I've looked at pieces of mathematical art, I've always been wishing that there was more about the mathematics that went with it. I'd look at it, I'd find it quite fascinating, and I'd want to know more about the mathematics that would go with it. I wanted some text to go with it. And whenever I would look at mathematical textbook that would have some photos or drawings of three-dimensional geometrical forms, I always wished there was sculpture to display it so I could really see it in 3 dimensions. And even if I was looking at it online, on a video or something like that, it gets a little bit closer to being 3-dimensional, but it's still not the same as really having the object there in front of you. And so I'm riding in the car and I think to myself, well, you really need to bring the two things together. What you need is not a sculpture or a flat textbook, you need a 3-dimensional textbook. And so when I got to Enschede, I had conversations with members of the Bridges board who encouraged me to pursue it. And I put in a proposal and they agreed to have a exhibit at this conference here. So around the corner here is room 204, where there is a 3-dimensional textbook with some 35 sculptural pieces and some 39 pages of text. And so the pieces illustrate the text. The topic I chose was the Platonic solids. It had been something I'd worked with as a teacher for many years and made models to bring into the classroom to explain. And over the years, I found that it never seemed to cease that as I looked at these forms, I would continue to find surprising and delightful new relationships within the geometry of these Platonic solids. And so I decided to make that the topic of the 3-dimensional textbook. And that's how this exhibit came about. Fortunately, I proposed it for this particular conference because I live not too far away and it was possible to bring things here. Now, please raise your hand if you've had an opportunity to look at the exhibit on this floor. Almost everyone, good. So, and now just so I have some idea of who I'm talking to here, please raise your hand if you've at some point studied a little bit of projective geometry and a little bit of group theory, let's say. Good, almost everyone. This is great. So if you haven't, don't worry, you'll still get something out of this. If you take a look at the 5 Platonic, what this talk will be is not the 3D textbook itself, of course. For that, you have to go next door, and we can't all fit in. But what I'll do is be talking about that exhibit. If you look at the 5 Platonic solids, then you can quickly do counting of vertices and edges and faces and so on, and you can make a little chart of it, and you see that in the chart there's a duality. For the cube, you have 4 edges on each face and 3 on each vertex. The octahedron, 4 on each vertex, 3 on each face. And likewise, you get 8 vertices altogether and 6 faces, 8 faces and 6 vertices. If you interchange the words vertices and faces, you interchange the 2 forms. And if you, you look at that, and if you only see that as the numbers, then you wonder, well, why is that? What is the geometry? What is the spatial relationships that make it come out that way? And there's a number of ways of explaining it. Some are fairly simple, but the best way of really understanding it is in the context of projective geometry. And so in this exhibit, I give a little introduction to projective geometry, and in particular, these are just the charts of the numbers that I spoke about. And you can see there the duality between the cube and octahedron, dodecahedron, and icosahedron. And if you take a line, which you see rotating around the point P there, and allow it to intersect the horizontal line N, it'll intersect it in a point Q, and as the line rotates around P, the point Q moves. If you're rotating around counterclockwise, the point Q is moving to the right. And now you reach a certain point when it says Q at infinity. You reach a certain point when Euclid would have said, all right, there is no point Q, the 2 lines are parallel. And in projective geometry, however, you are interested in studying the properties of figures that are left invariant by projection, such as what happens if you do a perspective drawing where you have a point of perspective, which is the eye, or you have shadows with a point of light. And wherever you have a situation like this, you have finite points that become infinite and vice versa. If you do a perspective drawing of a railway tracks, you correctly draw it with the 2 rails meeting at a point on the horizon infinitely far away. So if you want to study the qualities of figures that are left invariant by projection, you need to include those infinitely distant points in your study of projective geometry. What qualities are retained? Well, if you take a square, for example, and you project it, it's no longer going to be a square. The distances are no longer equal. The angles are no longer equal. But your straight lines are still straight lines, so you still have 4 sides. It's still a quadrilateral. The projection of a circle is no longer a circle, but it's still a conic section, and so on. So if in the context of projective geometry we need to include the infinitely distant, you could imagine that point P as actually looking n-wise at a line, and the line rotating on it you could see as n-wise looking at a plane. And then the point Q is actually an end view of a line that's moving off. And as that plane rotates around and becomes what Euclid would have called parallel, this line Q actually becomes then a line at infinity. If you imagine now this floor and this ceiling as 2 planes that continue on out, then they still have a line of intersection. It's a line, however, that's infinitely far away, going all the way around us. And people are sometimes, at this point, say, oh, well, then it's not a straight line. It's a circle if it goes all the way around us. But it is still a straight line, actually. It's just that if you look at it in that direction, you're looking at one side of it. And if you look at it in the other direction, you're seeing the same point from the other side. So you have to, if you work with projective geometry for a while, you develop an ability to visualize things in such a way that you include the infinitely distant in what you're considering. And once you do that, then what you get a duality arising. In Euclidean geometry, any two points have a common line, but two planes may not. They could be parallel and not have a common line. In projective geometry, they do have a common line. So if you take in projective geometry, interchange the word planes with points, any true statement you have in general about the geometry is still going to be true. You get a duality to it. There was a theorem of Pascal regarding conic sections, which was proved in the 1600s, and Briançon discovered an entirely different theorem in the 1800s. And once the principle of duality was discovered, it was realized these were just dual theorems to each other. And then as soon as one theorem is found, the second one's found, which cuts your labor in half, you know. So it's really a useful thing for mathematicians who are lazy and want to cut their labor down. So we have this principle of duality. However, duality tells you that a general statement can interchange points and lines and still be a true statement, but it doesn't give you specific points to associate to specific planes. I said interchange points and lines. That would be in 2 dimensions. I meant interchange points and planes. So if you want to find a way to find particular planes corresponding to particular points, then you need a function called a polarity. And within the exhibit, I show some plastic models that show you how to do this. And you can do it with a sphere, and as a point gets near to the center of the sphere, the polar plane moves further away. As the point moves out, the polar plane gets closer to the center. So the polar of the center of the sphere becomes the whole plane at infinity. And if you do that, then you consider then, since every form will therefore have a polar form, in which what's a point in one becomes a plane in the other and vice versa. And then you say, okay, let's take our Platonic solids and see what the polar forms are. So we see here a model which is in the exhibit, and you have a brass octahedron, and suspended in there is a aluminum cube, and the actual weighing, they're not actually touching each other. The metal doesn't touch the metal, but they're suspended from one another with strings, white strings, that actually form, maybe you can recognize the figure. Anyone want to say what it is? Well, it's hard to see in the figure, I guess. But they actually form an icosahedron, those white strings. If you look at it in the exhibit, you'll be able to see that. And so as you adjust the relative sizes of the two, they can stay polar to one another. If you have a sphere and a cube, you get a polar tetrahedron. Now, as the cube gets larger, I said tetrahedron, I meant octahedron. As the cube gets larger, the octahedron gets smaller, and vice versa. So you can adjust the relative sizes of the two while the polarity is retained. And by doing so, you find all these interesting geometric relationships between the two figures. And therefore, we can do the same thing with the dodecahedron and icosahedron. Here, the icosahedron on the outside in brass has strings, wires run across them diagonally, and aluminum tubes suspended on them to create, it's a little hard to see in the photo, it's easier to see in the exhibit, to create the dodecahedron on the inside. It makes it very clear why we had these dualities of numbers. Now, what I wanted to do in my whole design of these forms was to try to engender in the viewer the experience of these lines and planes coming from the infinite distance, so that this sense of experiencing things in the sense of projective geometry was developed. And that's why I chose to build from the outside in, and chose to emphasize the linear with use of tubes instead of solid material. And now, since we can now adjust the relative size, if the icosahedron is made much smaller, between the two there's this sphere of polarity. If the icosahedron is made much smaller, brought inside that sphere, then the polar form, the dodecahedron, is going to have to grow and become outside the sphere. And we get then this form, which is also in the exhibit. And again, it's a little bit blurry because of my old computer here not having the right kind of connection. But here you have the dodecahedron on the outside, and you put the diagonal wires in, put tubes on it, and you get the icosahedron on the inside. So now these two guys are dual polar to one another. These two are polar to one another. And clearly, if we take the tetrahedron and we ask for its polar, we're going to have to get another Platonic solid. So we're missing one. There must be 6, and Euclid was wrong, and David Riemann was wrong in saying there are only 5, because clearly we can take the polar of this and get another one, only what happens? You join up the midpoints of the edges here, midpoints of the faces, and you get another Platonic solid indeed, but it's just another tetrahedron. It's polar to itself. And the fact that it is polar to itself and is the only one that is begins to give a hint of the very special role that the tetrahedron plays. And I see I'm running much more slowly than I intended, so I will try to speed up a bit. You can look at the rotations of these figures to study the symmetry of them. So cube, for example, has an axis here of order 4, or here you can rotate a quarter of the way around and it still is the same, and you get axes of order 3 and 2. And in the exhibit there are models showing the axes of rotations of each of these Platonic solids. So you get one group for the tetrahedron, one for these two, and one for these two. The remarkable thing is that if you look for any finite group of rotations that are actually three-dimensional, we say irreducible, and you ask what are the possible groups you can get, it turns out that these are the only ones. And that's why, as we study all these different polyhedra in these conferences, we always come back to looking at any particular one and saying, well, which symmetry group is it? And it's going to be one of these Platonic solids. So the ancients found that these Platonic solids were very special. They gave us the only possible convex regular polyhedra, and in modern geometry we find that they're special in that they give us the only three-dimensional finite symmetry. So it's just another way in which we see that in contemplating these figures, we're really experiencing something quite fundamental about the nature of space. In this next model, what's happened is I've combined the last two figures I showed, the last two slides I showed you into one. There's a dodecahedron on the outside, and inside that is icosahedron, and inside that a second dodecahedron. You actually have a reduction by the cube of the golden mean from the outside dodecahedron to the small parallel one inside it. And so this figure is in there in the exhibit as well. And since it reduces by the cube of the golden mean, one can ask, well, okay, there must be some others in between. which reduce only by the golden mean itself each time. So you should have to be able to find the inside and outside dodecahedron suspended with two other dodecahedra in between. And that's where the cover of the art exhibit catalog for this conference comes from. This photo here, taken by Jason Pogachnik, of a model that you can see in the exhibit next door. Now, there's these Platonic solids give you a way of introducing more advanced mathematical concepts in ways that are very concrete. I talked about projective geometry as one example. Another example is group theory, which I've started to just touch on in speaking about the groups of symmetries of these. But also, it turns out the tetrahedron can be aligned with any of the other Platonic solids so that all of its rotation groups, all of its rotations are also rotations of the one that it's aligned with. And in this paper model done by Steve Morse, you can see, for example, this red tetrahedron here, and the whole figure is called a compound polyhedra. So there's 5 tetrahedra, and the outside points all give an outer form, which you can see quite readily is actually a dodecahedron. And if you were to take any rotation of, say, this red tetrahedron, you would also have a rotation of the whole dodecahedron. So it's a subgroup of the group of rotations of the tetrahedrons, a subgroup of the rotations of the dodecahedron. There's 12 rotations of the tetrahedron, 60 of the dodecahedron, so we say it's a subgroup of index 5. And it's not so easy to first grasp the concept of subgroups and cosets and Lagrange's theorem that the number of elements in the subgroup has to divide the number in the whole group. But with something with this, it's always easier to grasp concepts if you can make a picture to go with them. And here you can really picture what those cosets are, because if you think of the red tetrahedron and the group of rotations of it, and that makes a subgroup of order 12. So there's 12 rotations of the dodecahedron that leave the red one fixed. There's one coset of that subgroup of 12 more that move it to the yellow, and one coset that moves it to the green, and one to the orange, and one to the blue. And so that gives you your 5 cosets, and it becomes quite vividly clear, and you can write down, algebraically, exactly what each of those 12 sets of rotations are. And so it gives a way of making quite vivid some pretty abstract principles from group theory. This is the same figure, only you can see through it to see that what the intersection of the 5 tetrahedra are. Each tetrahedron is done here in brass, and the outside wires show the dodecahedron, the inside aluminum tubes, the icosahedron, which is the center of it all, the core of the whole form. And this is actually a tensegrity figure. The 5 tetrahedra don't touch each other. They all support each other through the tension on the wires. So that's the compound of 5 tetrahedra. I'd like to make some acknowledgments. I thank the Bridges Board for encouraging me to do this, especially George Hart, who served as liaison to the Bridges Board and helped me formulate the proposal. And I'd like to thank the late Georg Unger of Dornach, Switzerland, who originally, 45 years ago, suggested I look at Platonic solids in more detail. And I'm probably forgetting a few thank yous, but the Shapeways did the 3D printing of the joints. Metro Plating in Kensington, Maryland did lacquering and plating of the models. Jason Pogachnik took the photos that you see in the proceedings and in the catalog of the art exhibition. And Iris Levin is making a website for this, which already includes It's martin11.weebly.com. It already includes all the text, the 39 pages of text from the exhibit, and will later include photos of the models and a video which is being very kindly created by James Sullivan as a wonderful contribution to this, so that people will be able to see something of it online. And I'm not allowed to mention to you, because my wife asked me not to, so I will not say anything about the tremendous support that she has given and how much I have learned from her in the way of how to look at things artistically. I've probably forgotten a few thank yous I owe. Especially to Bob Rawlings, who has made these wonderful Kepler-Poisson models that I haven't had time to speak about here, and to Steve Morse, who's made the paper models. Are there questions? So 5 minutes, right?
Yeah, questions.
In the back.
I'm interested in knowing how the metal rod joints, how they seem to be very well staying together. How does it work?
For many years, I made the joints by bending little wires, and from each tube to the next tube, I had another wire, and then I had to have forms, temporary forms that were destroyed afterwards that held it all in place while the glue set. And you had to have a slow setting glue so you could get everything together first. But that was tedious and didn't give me as much precision as I was after. And then 3D printing came along, and Carlo and George both gave me some help getting started on how to do 3D printing. And now the joints are all made by 3D printing. If the outside is triangular, is triangulated, I can use a nylon joint. And so it's basically the shape of the joint with some prongs sticking out that go into the tubes. And if it's not a triangulated polyhedron on the outside, then I have to use steel 3D printing for it to make it rigid. And I always begin from with most of the models, I begin from the outside and work in, again, to give this sense of things coming from the periphery. Did I answer your question? That means I'm done. Is that what that buzzer is?
No,
Yes.
no, no.
Oh.
No, that was my mistake.
Oh, okay. I thought that was like vaudeville, you know.
Did you give any formulas or ratios for when you went smaller with one thing and out?
Yes, I have in the exhibit. There's a series of 5 models, and in the text it's explained that they progress actually by the golden mean ratio. So, why did I do that? Not because I love the golden mean, because it's represents divinity or something like that, but rather because if you do that, you just get all these interesting geometric relationships. So if you begin with the 2 crossing each other, and then you let one get larger by the square root of the golden mean and the other smaller by that square root, you then have a ratio that's increased by the golden mean. And if you study those 5 forms in there, you'll see you get all these interesting relationships, which is why you ended up with that cube of the golden mean and the one I showed you. I guess I have time for another question. Yes, Eve.
Is the icosahedron essential for the structure to stay together like that, or does the tensegrity work without the?
Oh, that's an interesting question. I built this actually with a scaffold, which was a larger dodecahedron on the outside, and I had radial wires that got removed afterwards that held the whole thing in place until I had the 5 tetrahedra built, and the outside dodecahedron wires all in place in tension to hold it all. I took off the scaffold. I had no idea what was going to happen next, and the thing was sitting on my workbench with these 5 points sitting down, so they weren't moving, 1 point from each tetrahedron, and the whole thing was a spring. You could go and that was theoretically it should have been rigid. But there's a little flexibility in the tubes. And so I could go like this, and it would go like this. It was like a clock pendulum. It would keep swinging for some time. And then I added the black wires on the inside, black strings on the inside, There's actually 2 going through each tube here, and they go to the golden mean points of the opposite edge here. And everything has to be done with a lot of tension. It's the only way to make it. And the trick is to be able technically to get the tension in it. And then once I put those in, the whole thing became stable, and it didn't vibrate anymore.
So those wires in the inside are essential, but the actual icosahedron is not essential.
Well, it's like saying you have an arm without a bone or something. It's because as soon as you put these wires in, as soon as you put these, I could have made it without the black strings or the icosahedron. But once you put the black strings in, you've got an icosahedron in the middle. It's just there. I just put the tubes on it so you could see it.
Right, right.
Did I answer your question? Okay. I think I'm done. It's Carl's turn. I'll just leave these. Carl?
Yeah.
Are these going to be in your way?
No.
Okay. Thank you. Thank you. I still remember my visit to
Okay,
your office.
my talk is also about the Platonic solids, and it's a real puzzle for when you get bored with what I'm talking about. I guess I need another little piece of tape. 2 of these will hold up into the tetrahedron, or the skeleton of the tetrahedron. 1 won't. The hero of my talk is this one. Well, I'll tell you, it actually, you can see it here folded up into the tetrahedron. One of the others does not, and one of the others does fold into the tetrahedron. A good bit of the paper that I wrote is a proof, which I think would be boring to go over. And I kind of think that what tends to be a little more interesting, perhaps to you all, might be what the connections are between this kind of mathematics and dances that we've done in our dance company.